My name is Jan van den Heuvel. I'm currently head of Department of Mathematics here at the London School of Economics, and I'm chairing tonight's session. It's my great pleasure to introduce today's speaker for this public lecture organized by the Department of Mathematics and the LSE. Today's speaker is Professor Paul Embrechts. Paul is an emeritus professor from ETH Zurich. ETH, the Swiss Federal Institute of Technology in Zurich. And Paul used to be, well, still is emeritus professor in insurance and financial mathematics. You might, when Paul starts talking and you listen to me, realize there's some resemblance in the accent we have, because we realize we speak the same language. But we were born in a different country. Paul was born and educated in Belgium. He studied in Leuven and Antwerp, the Flemish-speaking part of Belgium. After that, he had positions in several institutes in Belgium, but also a period of 2 years at Imperial College here in London. So he knows the city quite well. And after Belgium, Imperial College, Belgium, and then in 1989, moved to Zurich, where he has been ever since then. Although in the meantime, a large number, if you go to his website and you look at his CV, a very large number of visiting positions. Paul is also honorary fellow of quite a number of learned societies. He has at least 4 honorary degrees. I could count quickly on his CV. And all between all those activities, he also managed to do science. He's the author or editor, co-author or co-editor of at least 7 books, more than 200 scientific papers, lots of public lectures, lots of kind of writings for a general audience. So very much somebody who deserves to be invited to give a public lecture here at this place. So we're very proud to have him here. Please, if you want to tweet about this, you're more than welcome. Hashtag LSE Embrechts. For the rest, please put your mobile phones on silent so that we don't have an interruption during the talk. We also prefer in these public lectures to kind of keep the questions until the end. So after Paul's lecture, there will be plenty of time to kind of ask him questions about his talk, about his general kind of knowledge. So the notes I was given as a chair, so that at this point I should briefly describe what the speaker will be discussing in the lecture, which I find a little bit weird. When somebody is giving a lecture, you should allow them to discuss what they're giving. So let me kind of just let Paul start giving his lecture entitled January 31st, 1953 and 9/11, Living with Risk.
Thank you. Thank you very much. I think it's a great pleasure being here. Sorry, my voice is a bit going, but that's So the title of my lecture, January 31, 53, 9/11, Living with Risk. First, let me say a couple of things about the title. Why do I choose this particular title? Well, we could start with risk, and we could look at various ways of the way risk is defined, the etymology of risk. And one way you could do is from the ancient Greek, ritza is root. And it's used in Latin also for cliff, and also Homer, I think, was also keeping his hands off the root of a tree in order not to fall off the cliffs, etc. So that's where ritza comes from. So it's used in Homer's account of Odysseus' travel through the Strait of Messina between Scylla the rock and Charybdis the whirlpool. Later it became a nautical interpretation as hazards of sailing along rocky coasts. I think that's the more modern interpretation of risk. And I think today when we say to be between Scylla and Charybdis, I think the meaning is that one is caught between 2 equally unpleasant alternatives, which is, I think, nicely explained in this particular cartoon by James Gilray in 1793, where you see the William Pitt sailing Britannia in a little sailboat Constitution in between the 2 cliffs, the 2 perils. I mean, the cliff of democracy, the rock of democracy. This is the French cap of the revolution. and the whirlpool of arbitrary power is the inverted crown. And of course, the ship tries to find its way to the heaven of freedom and equality. And of course, some ministers are swimming behind there, and so that's sort of a pictorial representation of, I think, of risk in the sense of Scylla and Charybdis. So this is just a little intro of one of the possible explanations where risk may come from. But the real question I think I should now immediately address to you is, why do I mention the date January 31st, 1953, and my friends in the audience, of course, they know the answer very, very well, and all the Dutchmen in the audience should know the answer very well. Sorry. But it's not this answer. Indeed, I was born 2 days later, or 3 days later, in the village of Schoten, which is a nice little village close to Antwerp. This is where I was baptized. This photograph of little Paul at the age of 6, I think, was taken just off the church here. And this is the wonderful Our Lady's Cathedral in Antwerp. But I don't think that's famous enough, even now giving a public lecture at the London School of Economics. That's enough fame, I think, to claim that's the importance of that date. Now, if you would have listened to the radio program on Hilversum that night, the first one was at 6:15, you would have heard the following statement. This is the KNMI, the Royal Dutch Meteorological Institute. Over the northern western parts of the North Sea, a strong gale rages between northwest and west. The storm field is extending further. It is expected that the storm will continue whole night, and given this fact, this afternoon at 5:30 p.m., the areas of Rotterdam, Willemstad and Bergen op Zoom have been warned for dangerous high water. That was repeated a couple of times during the night, but this, of course, is very much pre-internet, pre-social networks, pre-whatever you call it. Meaning, as was usual in those days, at 12 o'clock, the radio shut down, and in Holland, the radio shuts down by sounding the Wilhelmus, which is a Dutch national anthem. And that was it. This was the last radio warning to the population. The storm hit with really devastating force a couple of hours later. And the consequences were absolutely devastating. These are just some pictures, and of course I come back to that, but you must see on this side of the dike, there's infinitely a lot of water where it flows into. That's the nature of Holland, but I'll come back to that in a minute. The consequences were truly cataclysmic, and I think some of my British friends in the audience, like Nick, we talked about that. In the Netherlands, 1836 people died that night. A further 585 died across the east coast of the UK, at sea on the west coast of Flanders. For instance, the ferry MV Princess Victoria sank with 133 passengers on board east of Belfast. There was further a large loss to livestock, hundreds of breaches of dikes, and huge loss to housing and farmland. So that, of course, is the 31st of January 53 up to the 1st of February 1953. Here you see a picture, and this is Zeeland, the southern western part of Holland. This is Belgium, starting Belgium with the Westerschelde, part of Holland. The Oosterschelde, that will play an important role here in a minute. This is Schoten, just northeast of Antwerp, east-northeast of Antwerp. And you see the water the nights I was born, or just when I was born, or was lying in maternity. I mean, it just sort of reached my feet, but not more. But you see there was a lot of flooding all over Holland, the west coast, and that's where all the casualties took place. Now, you must realize that in Holland, 21% of population live below sea level. Now, today over lunch, Johannes, are you here? Yeah, Johannes, he said you should not mention percentages. You should mention the real numbers. So we're talking about 3 million people, 2 to 3 million people live below sea level. That was a good remark you made during lunch. Never mind, 26% of land is below sea level. I'll leave that a percentage. There's a place called Nieuwekerk aan de IJssel, which will play an important role in a minute, where we are more than 6.5 meters below sea level. And that's this place here, close to Rotterdam. So this is really having an extreme important interpretation of living with risk. I mean, the Dutch for centuries have been living with risk and continue to live with risk. And I would like to mention some of the work I've been doing and some of the interest I've had in this field and how it sort of spurred on my own research in this broader area of such events. So I'll come back to that in a minute. And here's just one example already. Oh, by the way, here you see, I will not go into detail what is mean sea level, because you have the tides, and NAP is normaal Amsterdam's peil. You can go to Amsterdam, it has now slightly changed, but you can go to Amsterdam, close to the center of Amsterdam. This is the NAP. It's a modern NAP. This is Guus Balkema. Some of you may know Guus, who's a collaborator of mine and of ours. I'm climbing up the stairs here because it's interesting to see. If you go to that museum, you see the NAP, but you see also two columns of water, where the water level stands at that moment in time in IJmuiden and Vlissingen, which are two cities at the coast. And it's pretty high. It also shows you where the water stood, but you have to climb a bit higher. Where the water stood in 1953 that night, let's say at Vlissingen, it stood at about 4.5 meters above we are standing here. And here we're standing really the center of Amsterdam. That mathematics can come out of those discussions, I will not have time to discuss in this general talk, but at least I can say, well, we wrote a book in 2007, Guus and I, on high-risk scenarios and extremes, a geometrical approach. So there's talking about these extreme events in one way or another implies a lot of interesting mathematics. So the question the Dutch were faced with, and of course also the people in England and in Great Britain. So what to do next? Now you can go into the literature and you see one possible solution, which is what the Dutch did, is the Delta Project. And I will discuss with you the Delta Project. By the way, part of that I will show you which part is called one of the 7 wonders of the modern world of engineering. I will show you which is that particular part. But of course, you could think that the solution was not to be found on the left. There's a famous little booklet, Hans Brinker and the Silver Scales by Mary Mapes Dodge, an American writer, where you see a little boy, and this became a famous little boy in Holland. There are statues all over the place there, where he stops the sea from flooding his village by putting his finger into a dike. Now clearly this is not the way the Dutch solved their problem, but, and this is where history is one of these marvelous coincidences, something very similar happened that night. And this is on the right here. Remember I showed you the map here, Nieuwekerk aan de IJssel. The main loss, I come back to that later, was in this area. Most people died in this particular area by the flooding of the Oosterschelde into these areas. If a particular dike would have been breached at that point, instantly more than 1 million people would have been at peril. I'm not saying really of diamond, it would have been a catastrophe at that point because of the very low part of Holland. And this is exactly what happened here. In that night, there was a breach there at Nieuwekerk aan de IJssel, where, in a very courageous act, some seamen maneuvered a barge. Remember that night it was also storm force 10 to 11. Maneuvered the barge straight into the gap, and then judiciously really turned the right moment, and it was really sucked into the gap, blocking that gap, and that really saved. It's difficult to say how many people, but it really made a major difference. Now, if you go to Holland, to that area, you can find this commemoration of that, and the commemoration of that, and Jan will understand what I mean immediately, that statue that celebrates that event, which is not too far away from here, I'm afraid. It's called een dubbeltje op zijn kant. And in Dutch, if you say een dubbeltje op zijn kant, that's this here. And dubbeltje is a 25-cent piece. Sorry?
10.
Cent, yeah. 10 cent, sorry, 10 cent, yeah. 10-cent piece. And if you throw it, it's agony for every first course in probability. Remember, you stand there in front of your class, you toss a coin, you want to start with your first trivial model, and the coin lands on its side. And then you better walk out and ask somebody else to teach the course. If this happens with a 10-cent piece, that's called a dubbeltje op zijn kant, an extremely rare event. So I think this is one of these wonderful things that happened around that particular night. So the Delta Committee came about. Now let's look at the mandate. This is already in 1953. The mandate came in February already. The same month. The Dutch government gave the following mandate: which hydraulic engineering work should be undertaken in relation to those areas ravaged by the storm surge, and also to consider whether closure of the sea inlet should form one of these works. The first I will not discuss, because if you go to Holland, a lot of the dike works are behind the dunes. These are hydraulics works. That's where also, by the way, that's where also if you go to the Dutch coast, that's why all these windmills are there. A windmill is not a dike. It's a hydraulic system powered by wind. So that was, but I will say a bit more about this here. Can we, for instance, in the major area here, could we, let's say, close off the Oosterschelde, where most of the people, the highest number of casualties were found? Can we just close it up by a closed dike? So this was the mandate given for the Delta Committee. Well, the solution was found, of course. Now I go into fast mode. The Dutch built their dikes, and I only will mention two of them, and one in particular. So these are the 13 major dike constructions under the Dutch dike Delta project. The major one is here, the Oosterschelde Dam. You see, this closes off the inlet to the Oosterschelde. And the second one is the Maasland Kering, which is the one that really blocks off the harbor of Rotterdam, for obvious reason. The Maasland Kering, just two words about it. This is two arms, and now I think a little bit of the Thames barrier. The Maasland Kering are two barriers, the size of the Eiffel Tower each, that close. The Thames barrier, I saw it this morning when I flew in. It's really massive. And I first, preparing my talk, I learned that the engineer who came up with the construction and the shape, you know, it's like that. It's sort of semicircle. He got it from the shape of the knob on his gas cooker. That's the story, all right? I don't know. Just that happens when you prepare public lectures, I'm afraid. But it's a very different construction. It closes very quickly. I think it's 15 minutes. The Thames barrier can close, whereas this takes much longer. But anyhow, they're different constructions, different topographies, I mean, very different. This is the thing I'm going to talk about a bit more. This is the Oosterschelde Kering. And by the way, that's the one that is one of the 7 wonders of the mechanical world. That one. And what's the story? For the Oosterschelde Dam, the work already started in the 60s, because it was clearly that was a main threat. It was originally a closed dam. It was only completed with sluice gates in '86. So why did they change from a closed dam to sluice gates, which can open and close? And now you must think we're talking about 1950s, 1960s. Environmental. The Oosterschelde, of course, is the sea inlet. It has a large fishery industry, etc., fauna and flora. And the Dutch already in the 60s came up with a protectionist view on the Oosterschelde. And the government went for that with a massive increase of financial consequences. So that's the Oosterschelde. And they wanted to find a construction that keeps the tidal movement, but also, of course, safeguards the Dutch population. This is the solution. 9 kilometers, 65 concrete pillars, and 62 movable steel doors, and I said this is one of the 7. All right? It would be nice for you to think yourself a little bit what would be the other 6. But Wikipedia will help you. Important, now I go a bit closer to some of my interests. When do these sluice gates close? These sluice, this is a photograph I took myself at the conference of extreme value theory, EVA conference. We went to this area, it's called LSE Events. Visit it. Go there once if you go to Holland, visit LSE Events. It's wonderful, you can cross the dikes. Here you see the level above NRP, I mentioned what NRP is roughly. If the water level at a very particular point out that's at the coast goes above 3 meters over NRP, the sluices close. So once it's 3 meters, they close. It takes much, much longer than the Thames barrier, but it's a quite different construction also. The Thames barrier is a couple of 100 meters. This is 9 kilometers. This is where the water stood in 53, 4 meters 20. Of course, there were no sluices here. So you can imagine if that wall of water from the North Sea, standing at 4 meters 20 above NRP, mean sea level, flushes into your country, of course, it has to be a disaster. Queen Beatrix in October of 1986 made these very famous statements. This is for the moment just for Jan. De stormvloedkering is gesloten, de deltawerken zijn voltooid, Zeeland is veilig. I.e., the dam, the Oosterschelde Dam, is closed. The delta works are finished. Zeeland, which is this area of Holland, is safe. Everything is correct till, well, this is clear, it's closed, we can close it, and it has been closed much less than if you look at the closure of the Thames barrier, that's been closed much more often. Let's say once or twice a year or every 3-4 years, so it's much less closed. You cannot say that it's finished, of course, and I'll come back to that, because this is still the Delta plan in 1950s, and there will be a new version in 2017 I will talk about towards the end of my talk. Now, how are these dikes? I will now show a little bit of mathematics. The dikes around Amsterdam and Rotterdam, which is called the Randstad, which is the main area. They're calculated, their heights as a 1 in 10,000 year risk quantification. So the maximal flood, maximal sea surge at a particular point over a year period should be 1 in 10,000 or less. That's and it's called the Dutch measure. Okay, so we definitely talk about the extreme rare events. I think if I'm right, the Thames barrier is standing at 1 in 100 years. Though new calculations have brought up, I think it seems to be standing at 1 in 1,000 years. But you see these calculations of risk measures, how to infer from risk measures heights, is a little part of the whole construction. The main part is engineering, let's be very clear about that. But without mathematics, even if you build the sluices, how high do you set the sluices? There must be a measure there. And this is where the mathematicians come in and the economists. So the important were, first of all, a cost-benefit analysis, which was new in the 50s, 60s, by Jan Tinbergen. Jan Tinbergen was the first Dutch, well, not just the first. He was the first Dutch Nobel Prize in economics, but it was also the first prize in economics, Tinbergen. And a stochastic risk model by the statistician David van Danzig. And they combined very strongly in coming up with how do you even start on such an approach for such an enormous piece of work. And I should say that they took into account their collaboration, meteorological, geological, economic, societal, political, environmental factors, which I think even from the point of view today, I think is wonderful. It's clear to say that in this case, scientific collaborations were extremely relevant. They were not deciding, because in the end you will see who decides. Well, the politicians in the end, or you, the taxpayer, all right? But we have to guide the politicians, although it's not always easy, but at least we can try to guide the general audience. As a consequence, it was basically Jan Timberg at some point said, 1 in 10,000. Let's stop fussing about discussing that aspect. The actual dike heights very much depend on the location, it's clear. Once you go north, it's less, but let's look at around Amsterdam, Rotterdam. If you look at the paper of Van Danzig, I can give you the quote later, there's only one quote he makes of a dike height in his paper. It's 6 meters 73. So that's the quote that Van Danzig, with his mathematical calculation, made for the dike height, let's say, of the Randstad in the Oosterschelde. He knew that was, and I come back to that, of course, there's a lot of non-robustness in these calculations. He knew that there's a lot of variability. So he was willing, but that's not so much mentioned in the paper, but in the political discussions, to go for 6 meters. Then you can read the documents of the government, and interesting from these documents are 2 or 3 things. First of all, they lowered the estimate to 5 meters. Not on mathematical basis, but on cost basis, whatever basis. But at least Van Danzig gave a way of coming up with a solution, Van Danzig-Timbergen, and I'll show you a little bit of the formula they've been using. The government did not want, and it even mentioned explicitly in some of the documents, they didn't want any discussion in the documents on uncertainty. Which is really amazing, because if there's one thing that drives a lot of these things, parameter uncertainty, quantity uncertainty, no way. This is the number we will put to the parliament. And also, they were very reluctant to discuss even the meaning of the 1 in 10,000 year. That's clearly in the documents. So it was like a deus ex machina. So this is the solution, and we go for 5 meter, which is roughly a 1.15 meter increase of the pre-existing dikes at certain areas. Now it's interesting, that's just an after the event, and I come back to the Delta Project 2017, that the 1 in 10,000 is now moving to 1 in 100,000 because of climate change. And it's rather remarkable that with all the updates on Van Danzig's work, this is getting very close to what Van Danzig originally proposed, the 6 meters. By the way, remember 6 meters 70 was also the lowest point in Holland. So it's a bit symmetric in that sense, but that's just by pure coincidence, I think. If there's one thing you have to take away from my talk today, is an absolute necessity, research-wise and society-wise, to think about such problems in an inter- and multidisciplinary way. And let me say a little bit about that, if I'm allowed to. Did I do something wrong, or can you assess? Is there? Oh, I can also do it here. Oh, it's okay. Oh, it's blocked, I think. Yeah. Okay. I'll get you. Okay. Yeah. Okay. It will work. Let me just jump into one little piece, the Van Danzig paper. There's a mathematical formula. I copied specifically because even there was a discussion, I think, with the people from the computers, and say, well, perhaps it doesn't look very sharp. But no, it was just a copy from the paper. And it's a 1956 paper. Van Danzig, Economic Decision Problems for Flood Prevention, Econometrica. I'm now talking to the economists in the audience. I'll come back to that. The rather critical statement. Moreover, it was around 11 to 12 pages. Econometrica in those days. Just try to do that now. This is a formula. Now I just walk you through the formula, telling you which parameters enter there, not the derivation. That's the paper. The x in his formula is the dike increase above the existing dike. Okay, you have a point, you have an existing dike. The x is how much you want to make it higher. Okay. That's just a logarithm. There's a constant there I come back to, and there's an alpha there I also come back to. Then you see, so everything is driven by this constant. Now what's in this constant? And the only thing you have to take away in his derivation, in their derivation, well, this is mainly Van Danzig, all these things come together in the right dimensions, of course. In the end, you want to have meters. So that you have to be careful about, and that's all right. P0 is the probability at a particular point in time for a yearly exceedance of the existing dike level. Now, this is where the extreme value people in the audience say, oh, this is a bit like the peaks over threshold. And indeed, here you will have the exponential model, the exponential distribution for the exceedance probability over a given existing dike height, yearly exceedance probability. And the alpha here is an exponential parameter. So Van Danzig, and it's not a bad choice. Of course, you looked at data, very sparse data. But the exponential is not a bad model to start with, which goes back to a Gumbel distribution. And I could now give, Johannes, I could now give a completely different talk on a recent movie on Gumbel, but next time. The V, now comes the economist, is the value behind the dikes. This can be value in livestock, this can be value in land, this can be value in houses, this can be value in people. There are discussions of value of people. What is the value of life? It sounds a very unpleasant discussion, but it's an absolutely crucial discussion to have with the, and I think these papers are really wonderful in going through that. So that's a V, value. The delta prime is a discount factor because somehow dikes are built to withstand a certain period, and the period is typically capital T. Also, your Thames barrier has a life cycle time after which it has to be replaced. So in this case, that's the capital T, and the delta prime is how you discount money from, let's say, 50 years in the future to now. The beta, that's special for Holland, I don't know for the UK, but Holland is sinking. The mainland is sinking. At a rather slower rate now than it used to be. I forgot now, it's a couple of centimeters a century now. But Holland sinks. That means the dikes in some way get a bit higher. So there is a compensation for that also. But I only want to mention that. I think I got, oh yeah, the K is the cost factor for increasing the existing dike height with 1 meter. Now, it's not for me to discuss with you why does a formula look like that. But it's for me to convince you what the formula took into account, all these components. And this is a formula when you then put in all the variables and look also at some variability in all these estimates, which he clearly discusses. That then came up with the 6.73 meters, that Van Danzig. It has been criticized later. Of course, you can always criticize, but he was the first. By the way, the first that really started thinking in a more scientific way is Lorentz. If you look at Lorentz, the physicist, in the north, at the Waddenzee, the big dams there, in the beginning of the 20th century, Lorentz made early calculations there. But Van Danzig is, and now I was a bit critical, and I hope that the economists in the audience have noticed my criticism. That it's not so easy nowadays to write an 11-page paper on such a problem and have it published rather quickly in Econometrica. The economists in the audience may try it. If they succeed, let me know. But now I'll be critical to the mathematicians, to my own group. Why? Because Van Danzig in 1954 was a key invited lecturer at the International Congress of Mathematicians, giving a plenary 1-hour talk. Now, in order to give a plenary 1-hour talk at an International Congress of Mathematicians, you have to be damn important. He was asked. I don't think it's so quickly repeated anymore. And I think this is I think for both groups, I think the economists, what they publish, I'm not critical of what's now published in Econometrica. I mean, don't get me wrong here, but I would like to see also other work published. And I also would like to see some other lectures occasionally. Both are learning, but I think this is a wonderful example where both are so extremely present. I told you we'll go to the second mandate. I leave now the old construction. I mean, there's a lot you can discuss still there, but I hope it is, you see where the science can enter. Extreme value theory, I mentioned the peaks over threshold method and the statistical estimation and all these constants and the economics and the cost-benefit analysis. Now we move to 2007, there is a second Delta committee, the second mandate after the 1953 mandate. The government asked the Delta committee to come up with recommendations on how to protect the Dutch coast and the low-lying hinterland against the consequences of climate change. I mentioned before 1 in 10,000, 1 in 100,000. So climate change for the Dutch is now a major issue, not just for the Dutch. The issue is how the Netherlands can be made climate-proof over the very long term. This is important. Not just 3 words, but I'll come back to these 3 words. Safe against flooding, while still remaining an attractive place to live, to reside and work for recreation investment. That's the official mandate that the government put to the Dutch scientists, engineers and mathematicians, statisticians, environmentalists, etc. Now, hidden in these are several interesting, challenging questions. First of all, very long term. Well, in the environmental work, we're talking about perhaps 100, 200 years. How do you discount in such an environment? And I'll just give you a wonderful reference. There's much more there. Christian Gollier in Toulouse, Pricing the Planet's Future. The economics of discounting in an uncertain world. How do you discount? You can always say, well, we can't. Well, that doesn't solve the problem. Then somebody else will just put a number there. So that's cost-benefit analysis. Remember, the whole thing was built on a cost-benefit analysis of Jan Tinbergen. Now, if the environment enters, then you enter very quickly what Marty Weitzman called the dismal theorem. I'll leave that for the Q&A session. If you want to hear me say something about the dismal theorem, it's a very sad story, but you know that Weitzman died earlier this year in very tragic circumstances. I will not enter more into that aspect, but I think you should at least be aware that there's something like a dismal theorem that exists there. The value of life. I mean, how do you estimate the value of life? There's a whole discussion now going on. What is that? Definitely when you talk about human life. Okay. There's a new threat which is explicitly present in there, is cyber risk. Why cyber risk? For instance, the Marsland Kering has more than 100,000 lines of computer code to close it. So you don't have to be a criminal mind just to think what may happen there. Okay. And high quantize, you go to 1 in 100,000, non-stationary series, etc., etc. So this is a lot of interesting questions are hidden there. Okay, so I leave for the moment this part of the talk. Very briefly, why do I have 9/11 in the talk? Well, that's a very different kind of risk. And let me just tell you why I was very closely related with 9/11. So on September 11, 2001, I was invited to give a talk in the morning of 9/11 at the top floors of the North Tower, which was a tower which was first hit, for Risk Magazine. And it was for a conference on technology, Waters Financial Technology Congress. Unfortunately, I had to decline the invitation. Otherwise, not only would I not have been here to give you my story, but I think it's one of these events in life that happened. I got an invitation, I declined for a clear reason for me. I was not able to accept that invitation. All people present, because it were the 2 top floors, all people present from the conference died that morning. This is an extreme example. I think risk takes on a very specific personal individual meaning, I think defying very clear, obvious scientific elaboration. I mean, this is a very personal thing. Although it also, as a person, of course, as a risk researcher, it shapes your mind. It changes some of the parametric thinking in your mind about risk in life. But I will not go into further details about it. But this is just the 2 aspects in between which I've sort of shaped this talk. But of course, most of the work, scientific work, is the first part. Let me now turn to ETH Zurich. So you already mentioned Eidgenössische Technische Hochschule. It's a very nice university in the center of Zurich. Mathematics is the only only department in the old building, so the whole of G floor is mathematics. And many famous mathematicians were there. Let me ask the audience a question. I'll show you 2 students. And let's see whether you know the students, okay? This you should know. Who is this? Einstein. The more difficult question is? Von Neumann. Who said von Neumann? Yes, von Neumann. Very good. This is John von Neumann. He studied chemistry at ETH. All the professors were frightened of von Neumann because he was so incredibly fast in the lectures. So these are just 2 students that were at ETH. I think the fil rouge of my teaching at ETH the last 30 years is very much a mathematical understanding and public communication of risk, but also the mathematics behind. This is now going to be a book we are working on, from my point of view. Okay, but I will not go into detail there now. And some of you may know some of my books. There is Modeling of Extreme Events for Insurance and Finance, where you see some of these events. There's a book in the 2nd edition of Quantitative Risk Management, and in between there's a book of these applications into finance. So I've done quite a lot of mathematical work more in this field. And already in '97, the Extreme Value book warned the world of banking, insurance, and regulation. So I now move from the dikes to the banking world. And regulation for an insufficient understanding of extreme, rare, non-normal events. It took, however, a further 10 years, 97 to 2007, a black swan, and a financial crisis for that world to take necessary notice. And I'll just show you the black swan link. Of course, I think all of you know this book by Nassim Taleb on the black swan. But what I like about Nassim's, I will have a joint conference with podium appearance next year in Leuven with Taleb, so we just were on the phone yesterday. He's an interesting person. He wrote on Amazon, and you can check about my book the following. I'm very proud to read that together with you. This here is a book that grows on you. I would have given it 5 stars when I started using it. Today I give it 6, and certainly 7 next year. 5, by the way, is the maximum. But the kind of hyperbolic speaking here. I am buying a 2nd copy for the office. If I had to go to a desert island with true probability books, and I think my probability friends will enjoy this, I would take Feller's 2 volumes, which are written 40 years ago, and this one. So that's, I think, I feel extremely honored by that particular statement. And occasionally I do an experiment with my students. I say, go to my library, there's about 2,000 books or more. I say, look for the most worn out book in the library. They always find this one. This is Feller, my original Feller volume 2. And now I speak to my friends here in front, and I just go up, and for the mathematicians. This is a pure mathematical 1.5 pager, and I won't even try to go non-mathematical on it. If you go to Feller page 471, you see the following statement. If you have a survival distribution, which is regularly varying with a certain index, then the renewal function is also regularly varying with the same index, well, minus sign. A consequence, if you multiply them, this goes to a constant, depending on the alpha, on the parameter. Okay, well, if you know probability, absolutely 0 problem. If you don't, I cannot explain it here. But then comes an interesting statement on the next page. Feller says it's easy to amend the proof of this result and prove the converse. That means that if this holds, then also this holds. And you can make a very nice link with extremes and sums and all that. This is known as the Dynkin-Lamperty problem. And now my friends know what's coming. I was a PhD student, of course. This was my first problem I got from my PhD supervisor. Now here I am, 30 years professor at ETH. I was not able to solve my first problem of my PhD. So for the students, never despair, all right? Find another problem. My supervisor, Jeff, gave me the problem. Sid Resnick from Cornell early on wrote to me and said, Paul, do you see why the converse to this lemma is so obvious? And then I worked quite a lot with Nick and certainly with Charles. I remember Charles, we were working on the blackboard, always getting closer, but never were able to prove it. It's still open. So students, do not despair. ask your supervisor in time for another. The in time is relevant here. Now, let me go back to interdisciplinarity. At ETH, because of my position, I've been very much involved in bridging the gap between industry and academia in the world of insurance and finance. And I'm extremely proud till today that I founded in '94 Risk Lab at ETH. This is the German text. In those days, the three main banks in Switzerland, Bankgesellschaft, which is now UBS, Swiss Bank Corporation and Credit Suisse, together with us, supported us in what we called pre-competitive research, voorwettbewerbliche Forschung. So we were able to convince these companies to link up in a heuristic way to support research together with us in the vastly emerging field of finance and insurance. This is '94, the 7th of October, the publication. Now, how did we do that? Well, this was a setup. So this is ETH. In the beginning, we were mainly ETH and the three main banks. Later, we had Swiss Re and some other universities involved, but to a less extent. We asked for the regulators. I'll come back to the regulators in a minute. Bank for International Settlements, the Basel Committee, to come and join and discuss with us we had a whole day sessions where we said, what are your main problems in this area of risk management? What key can contribute? And by the end of the day, we voted together, these are the 5 or 6 topics we want together work on. And together means academia and industry. It's a blueprint for today, but it's very difficult to copy. It's hard work, but I think it did work. And I could give a whole talk now what came out of Risk Lab, but I think it really worked. I come back to another queen. I had the Queen of the Netherlands before. I think I cannot, slight tongue-in-cheek, repeat here what the Queen said in this house here in 2008, when Her Majesty was visiting the LSE in November 2008, just at the end of the crisis, well, after the crisis or the end, and referring to the crisis, she asked, why did no one see it coming? Well, it was a pretty obvious question. But from the Queen, I think people were really taken a bit aback because they had no real answer to that at the time. Did I have an answer? Absolutely not. But did I come close? I see some friends from the Bank of England. Did I come close from the regulators? Did we come close with some relevant warnings? Absolutely yes. And this happened in this house because you see here the Financial Markets Group. And we wrote a paper, it's called An Academic Response to Basel II. It's still on my website. It's officially submitted to the Basel Committee. It's on their website. It's at the website of the BIS. They all know it. You see the people from here, Charles Goodhart, Con Keating, not from, but he was a student, Felix Munich, Olivier Renaud, Hee-Young Ching. He was a professor of economics here. He then went to Princeton, is now at the BIS. So it was really an interdisciplinary group that wrote this paper. Let me just give you, and you can look at it, it's verbatim. I just took it from the first summary page. What did we say? So we're on, let me go back. We're now 2008. But we wrote this in 2001. So now think back what we wrote in 2001, what we said about the potential future and how yes or no regulation could prevent it. I put it a bit sharply now, but never mind. The new regulations fail to consider the fact that risk is endogenous. Okay, so within the system. Value at risk-based regulation for the specialists can destabilize an economy and induce crashes when they would not otherwise occur. That's a bit of a strong statement, but there is truth in that. Statistical models used for forecasting risk typically underestimate joint downside risk. Because a lot of the regulation was on one bank, not the joint default. That was a major. Too heavy reliance on credit rating agencies for credit risk models. We even wrote, I think, who rates the credit raters. It's all in the paper, and a whole discussion on that. These proposals will increase procyclicality and hence systemic risk. So make things worse when they're already bad. And finally, operational risk model is not possible given current databases. Now, you can now look at these statements, map them what happens today, what we know today. I think they were close to spot on. We did not foresee the crisis, so we could not give Her Majesty, the Queen, and say, well, we saw it. No, no, no. We said a lot of people are driving to a wall. I don't know where the wall is, but surely I can tell you the car has no brakes. You can read the paper and make your own opinion. And I think I'm very proud that I did that here. I was lucky. I was at that time, I think I was close to being here than before I was here, Centennial Professor of Finance, I think. But this was really exciting to do that together with and so we even wrote a conclusion that these regulatory proposals, now we're to Basel 3 and 4, will enhance both the procyclicality and susceptibility of the financial system to systemic crisis, thus negating the central purpose of the whole exercise. And this statement is there. Reconsider before it's too late. Let me finish now, I think I'm in time, with a quote on interdisciplinarity. So if I look back at the talk I gave, I talked about the Dutch dike example because somehow it made an enormous impact in my own research. Just by talking to people like Guus Balkema, Laurens de Haan, Wim Vervaat, Frank Steutel, my English friends, Nick Bingham, Charles Goldie, extreme value people in the world, I think somehow it was shaped, at least on the lower countries, a lot by thinking questions there. You have similar problems in different areas. I mean, take the Thames Barrier, this is just one example. Take the rainfall, which is much more difficult to model, rainfall precipitation. So the main point I want you to take along with it, that interdisciplinarity in many of these problems which are important for society are absolutely crucial. And I think we as a university, now I talk a bit more as a retired professor perhaps, but I think we should put more emphasis on interdisciplinary work. I think we all sin, in mea culpa, mea maxima culpa, by digging deep, but I think we should also try to dig a bit wider, and the system should allow that. I see some positive changes there, but I think it's absolutely necessary. So let's read this together. This is by accident. Again, this is by, don't read it yet. Well, you can't. It's the last slide. This is, when I was preparing the talk, I wanted to end with a statement which I think summarizes some of the feeling I have in this field. This is now something that comes from North America, USA, and has to do with flooding. Just to give you an example, twice I was phoned by the US. Once after Katrina, I was phoned up by the Army Corps of the engineers in the US, civil engineers. They want to ask me how these extremes, how can we use them? And then I was asked in New York from a radio station after Sandy. And there they asked me, how do you handle insurance in these events? Because that's something else. So let us read that quietly together. This is the last slide before I say thank you. And this is a quote from a paper by Goodall, a book by Goodall, The Water Will Come, Rising Seas, Sinking Cities and the Remaking of the Civilized World. Well, the sinking cities, remember, that was the beta in Van Danzig. Remember, sinking Holland. Not too much. Here it goes. It's just easy to talk. This is the US version. But wait till I discuss this here. It's easy just to talk about technological engineering solutions, but a lot of the problems surrounding sea level rise are legal and political. The Dutch have a legal and political system that is united around dealing with water issues. They've been doing it for thousands of years. Nassim Taleb would say they really have skin in the game, or their feet into water. Here in the US, it's not getting the right engineering ideas, figuring out what technology or design ideas we're going to use. It's that our legal system and our political system are just not adapted to thinking about sea level rise in any kind of holistic way. Now you can change in this statement, US by Switzerland, for instance. You can change sea level rise by pension funding. And then you immediately have a serious problem in Switzerland. you could take perhaps, shall I do it? UK and Brexit. And of course, you can do social networks, artificial intelligence, machine learning in certain countries. I just was in the middle of the major disruption in Hong Kong. I was there with my wife, staying on campus of one of the universities. I've never seen such an enormous influence of social networks. Because everybody asks me, who is driving the protesters? Of course, there's also the police there, both. I don't know. It was so clear that social networks have an enormous influence. So these are questions we should discuss in a holistic way, I think. Well, I think I've taken much more time than I think is deserved. And I think by this, I would like to thank you.
Well, thank you very much, Paul. I don't think anybody will argue about the time you took and complaining about it, because it was very interesting. I might be partly biased because of being Dutch. And on the map, when Paul showed where he was born, my mother was living on a similar kind of spot, exactly on the boundary of...
Yes, it was Bergen op Zoom.
Yeah, north of Berg. One way.
Yeah. Here.
Yep. So that's where my mother grew up. And she was 20.
Okay.
When it happened. Okay, enough about me. Questions?
Nick?
A question and a comment.
Sorry.
The ship you mentioned went down between Scotland and Northern Ireland with heavy loss of life. The storm then passed west to east across the top of Scotland. It then turned south and scoured down the eastern seaboard of the United Kingdom. When it got down to the Thames estuary, it came up the Thames estuary many, many hours later, and people were drowned in their beds on Canvey Island. I wondered for years and years how the authorities could have been so lax as to let that happen.
May I?
I have one answer which I will share with you. I believe it to be true. My PhD student, Tasmin Simons, now my collaborator, she's out there in Oxford now, was seconded to the Met Office a year or so ago, and she worked there for several months under the direction of one of the two experts in the Met Office on storm surges. This lady's opinion is because mankind back then did not understand enough about the hydrodynamics of storm surges. That, to me, is a wonderful illustration of the need for multidisciplinarity and interdisciplinarity. It saves lives. Thank you.
Can I make a Dutch link there too, because you can have the same question here. Remember, this is the verbatim, well, I translated from the Dutch. This is the verbatim text that went on from the KNMI, Koninklijk Nederlands Meteorologisch Instituut, your Met Office, the night of the storm, 6:15. Of course, then the storm, they knew it was coming from Scotland, of course, but there's also the whole topography of the inlet between Scotland, the Dutch coast, and so in England. Have you mentioned one point here? They wrote here, dangerous high water. They could have written very dangerous.
Yes.
It was in their power to do so. They would have had reasons to do so. I mean, it would have meant something.
Yes.
But it was dangerous. Why? Again, I think it might be perhaps I don't worry the people too early, false positive, false negative, it's a very difficult discussion. And the second thing, of course, but this is much more an issue in the Netherlands than it was in England and Scotland, because there it took a while to get down, but it was careful, it was the night. It was Saturday to Sunday. As I said before, there was no means of communication. You mentioned the people that died on these islands. these people were dying in their houses because somehow they all went to bed, and these are official stories. I mean, your family will know these stories, but they went to bed at midnight after the Wilhelmus. A dangerous storm is coming, but dangerous storms have been many of them. Well, several of them. This was a particularly dangerous storm, which was, it could have been a very, but I mean, I don't know, hindsighting here, I mean, it would be absolutely ridiculous for me to do so. But this was also a major issue. There was absolutely no warning. Now, I mean, our telephones will be flashing all over the place. Not in those days. But I think it's, well, it just shows that what you say, of course, the example of the cross-disciplinary thinking in these events, I think is extremely important.
No sirens?
Sorry?
There are no sirens that would go off? I mean, to alarm people?
Not as far as I'm aware of, no. Of course, in those days, the question was, there are no sirens, of course, in those days, these were farmlands. At the best, there could be church bells. But you have to trigger a church bell also. Now, there's no official, as far as I'm aware. No, it was very similar to what happened to some extent to the UK. Yes?
Please wait for the microphone.
After taking my degree here, I went on to do my national service. And in January 53, I was posted to Felixstowe, RAF Felixstowe, a former seaplane base on the north bank opposite Harwich, where Felixstowe Port now is.
No, I know Felixstowe very well. I used to go there from Zeebrugge.
I've never seen anything like it. I went on to become a risk manager. I'm glad that I never saw any other risk like it. I just thought I'd make that comment.
That's, well, what shall I say? I mean, I'm thrilled by your comment. And I mean, this is also something that I now have to retire at 65 at ETH. That's the mandatory retirement. I always say, it's a bit of a pity, man. Of course, I still function in many ways, but somehow, especially when it comes to risk management issues, keeping this kind of experience alive, even over a coffee table discussion with your younger colleagues, I think, I hope you still do that. Thank you for your comment. I think very nice. Thank you.
Thank you. Can I invite some more questions?
Yes?
Can you?
You can always ask the dismal theorem. That's a nice story.
Good evening. I've got a couple of things to say, actually. The first one is, when was the previous largest storm to the one that you talked about?
Yeah. I tried to find a picture where you can see that. I think it was about 15 years before. It was, I mean, there's a house, I know there's a picture of a house with from 1953. There are 3 marker levels, and I think they start sort of mid 19th century to up to 20 years before this event. I'm not sure when the distances were, let's say 20 centimeters, half a meter, something like that. But of course, that's very well documented. But that's, you're right, that goes a while back. And of course, there are very famous floods in the Netherlands, like they even have the names of saints, St. Elizabeth flood, etc. But you must also realize, in that flood, if that's the right one, in the 15th century or so, more than 20,000 people were killed. But of course, the defenses were quite different in those days too. So there is a bit of information there, yes.
My other interest is around earthquake and nuclear power
Yeah.
in Switzerland. Have you done any work around that?
Marginally, I've got a colleague of mine, Didier Sornet at ETH, and Wolfgang Kröger at ETH, who just wrote a book on risk management for nuclear power stations. In the whole debate around should we really shut them down or not. The only thing I can say is that we have done some analysis on nuclear power accident losses, and they're extremely heavy-tailed. I mean, massive loss potential there. But I myself, I've done some work, but now I go back to the very early days of my life, and I also do my recent work. There is important work by Ogata. He's a Japanese earthquake modeler now, using Hawkes processes, Alan Hawkes, where you have these models with initial burst, a high quake, and then aftershocks. That I've done quite a lot of work on, but more on the modeling. And then, to finish my answer to your question, I was once on Italian television after the Aquila earthquake. You know, the Aquila earthquake, 2000, Italians here, 2000, was it 1 or something? Well, the Aquila earthquake. The Aquila earthquake is it's a wonderful example for how bad things can go. Science, population, communication. You know, 6 people were jailed in the beginning because wrong information the night before. Stay safe in your houses. Now I come back to your point. There the discussions they had with me was related to insurability also, but now we come to Aquila. The earthquake was 6.3 in the end, I think. But the months before Aquila, there were hundreds of shocks, 3 up to 4. Now you must realize you're living in a medieval town. If you live in a medieval town, these little shocks, they really go to the substance of your building. And then you don't need the 7 or 8 to really destroy everything. So there I'm a bit involved in some discussions, but I'm not an expert. Thank you.
Further questions? A lady here. Oh, sorry.
Oh, the lady.
At the front, yeah.
But then also the gentleman there.
Oh, sorry. I didn't.
So when you think of the kind of evolving risk landscape, you mentioned cyber risk.
Yes.
But then there's another kind of risk when it comes to reputational risk, and I know that's quite an intangible risk.
Yes.
But have you ever thought of looking to quantify that?
That's a good question. I mentioned to you, I mentioned to you the example, I think, when we taught this book at the Federal Reserve in Boston. Remember the yellow book? Now you must look very carefully at the definition. It was for operational risk. Operational risk is the risk of loss in the banking world due to people, systems, external events, all right, including legal risk, and now it comes, but excluding reputational risk, because I think, and I didn't do research on that, but I discussed, I think I was in there from day one in the operational risk discussion in the late 90s. One of the statements was that some researchers from the Wharton made early on, when look at data, is if you have a reputational problem, the market will punish you because it's your reputational. If you have fire, okay, that's not your mistake. I mean, it's not immediately. But if you have a reputational problem, a really reputational risk problem, then of course your equity will go down. So there was this early discussion. I have stayed away from modeling that, and I even, if you saw in my statement, I have turned against using overcomplicated models even for operational risk. And now we could discuss cyber risk. We're now doing a course on that in Zurich. Let's see later. I mean, I also have my thoughts about that, but I think it will be a very major. The cyber risk, interesting thing there is now that the technology comes in. You have the networks of computers, and there's a lot of network theory there now used, disrenial networks and all that. So cyber has some interesting links to science here, but reputation, short answer is, after a long statement, is no. The gentleman had there.
Thank you.
Good evening. My question was mainly around, I think early detection of catastrophes is probably half of the problem. But once we have that foresight of a catastrophe, whether it's environmental or financial, how do we act upon that information? And how do we manage, for example, if we have an idea of a storm approaching, how do we evacuate a city or manage the panic?
Yeah, that's, well, for instance, let me just, a first small comment on that. If you look, for instance, at the difference between New Orleans and the Dutch coast. New Orleans, I think the levees are built, don't take me 100%, but I think it's 1 in 200 years, the levees of New Orleans. If you look at the Dutch coast, it's a 1 in 10,000 levee height, very roughly. A very first statement, why that? Well, first of all, is the time of the year these things happen. if you have a storm in the Netherlands, it will typically be January, February, it will be very cold. So if you're up to here even in water, you're dead within 15 minutes or less. If it happens in New Orleans, the thunders, the storms, that will typically be in summertime. So it will be quite different already temperature-wise. Secondly, the US has a much faster way of evacuating people just because of the way the US is constructed, whereas in Holland it's very different. These things enter very much in the discussion of the V, the famous V in the Van Danzig report, which is now, I think, looked at much more carefully. You just cannot evacuate, let's say, Delft or any small Dutch city the way you can, let's say, you all hit for the motorways in the US. So it is a determining factor in saying, should we go for one in so much, one in so much? Should we perhaps add a bit more? The early warning, that comes back to Nick. I mean, I can only hope that we know. It's already amazing how meteorology has improved itself. I mean, I should not mention, I think, the example. No, I should not. There's a famous example in bad prediction of a storm in the UK a long time ago. But I was even living in Brighton when the trees were flying around our head. But I think we have now much improved in that particular context. So there, I think I feel much more evacuating the state. Even in Holland, it will be very difficult. We're talking about pre-warning. I don't know, I'm not a meteorologist, but I mean, perhaps we talk about pre-warning, and you think of false positive and false negatives of a fairly short time. I think that is very difficult. It's different with tsunamis. I think tsunamis, there, I think, but again, you have the secondary effects. You know, things that's now for a risk specialist more than for me in behavioral science. You know that when 9/11 happened, and I told you that 9/11 somehow is sort of burnt in my mind for other reasons, the months afterwards, much less people traveled by plane certain distances in the US, and there was a spike in the number of people killed in road accidents, just because we have a very different attitude towards risk. So it's an absolutely crucial question. I mean, a scientist like us should be involved there, but I think it's not an easy one. For specific risks, we can discuss, I think, some precautionary actions, but it's not easy. And no, it's not a full answer, but I think it's a good question.
Thank you. Question. Can I just wait for the microphone?
Yeah, just.
Oh, thank you very much for your interesting talk tonight.
Thanks for being here.
So tonight I really learned that the modeling of risk is quite important, especially today with the risk of flooding and environmental. There was this article in The Economics a few weeks ago, I think, that was saying that there are all these new companies being bought up by big financial corporations. And it is precisely because the data are really important. So my question is, what is your idea? What do you think would happen in the future given the uncertainty in the climate and those data being in the private hands? What implications would it have on the inequality already in the world?
Okay, so you talk about climate data?
The risk analysis of the data.
Yeah, I think I also. The only nice thing about commuting to your work is that you have time to read on the train. So and I read The Economist diagonally, and some of these things in detail. So I read that article, and it's about companies that now sell these models, risk models. I don't know. It's like in insurance, of course. There's this famous example of the three main companies. I know the names roughly, but there are three main catastrophe modeling companies that all the insurers use and reinsurers use worldwide to calculate premiums for catastrophes. In all of these things, I must say, and I voiced that a couple of times, also in London here at meetings, I find it really not good that science is sort of precluded from the overall discussions in the quality of these data. I mean, I know this from the insurance world, the climate world, that's another matter. I may make a bracket if I'm allowed later to the dismal theorem here, because not far away. But yeah, I think diversity of modeling is important, openness to modeling, but I think at least openness to the models used. I think that is more important. And I'm a bit afraid that when these companies use their models in a secretive way, I'm not all that happy. I've seen examples of that in the insurance world, catastrophe world, where it didn't go well. But it's too early. I read the article, I'm aware of that. But
your suggestion would be more inclusivity with regards to scientific.
No, I think we have, especially in the climate world. I mean, look, in the risk center, I did not discuss the risk center at ETH. We do a lot of discussions on climate modeling. Now, of course, especially this week, these 2-3 days in London, there are definitely some people around who are not very positive with respect to climate change and all that. And you can always find somebody who says, no, there's nothing to worry about. You have to go back to Ronald Fisher and smoking and lung cancer in the old days. What we should teach the people, and remember the Dutch, it was explicit in the report of the government, we don't want uncertainty estimates. We don't want you to make a statement with 95% certainty. We should have the dike height between, let's say, 4.50 meters and 6.85 meters. They didn't want that. No, you give me a number. The same is true with climate. And now I quote somebody. If you look at all the works that are done by so many scientists all over the world, and you combine their estimates on uncertainty, we give statements like, and some people say, well, we have an increase in temperature over the next 50 years of, well, by the end of the century, by, let's say, 2.5 degrees. These are statements made somewhere. That's not a statement I want to hear. On the basis of these papers, you can now make statements, and people have them. They say, well, the best we can say now, on the basis of the research done, is that it will be with 95%. It will be between -1 degree and +8 degrees. That makes me worry. Then I think the politicians should really stand up, and not just Ms. Stoltenberg, but I think the politicians should stand up. Well, if that we get into that range with that kind of equal probability thinking, then we should act. And if it then turns out to be -1, fine. You see, this uncertainty has to come into the whole discussion. And I think too many of these things are sold as, well, this is the estimate, just price your product and that's it. And remember, even the Dutch government, although they're among the best in the world in those days, wanted to get rid of the uncertainty. And we should fight against putting the uncertainty in. But at the end of the day, we have to help to decide. And that's what Tinbergen did, 1 in 10,000.
Hey. I mean...
Is that the dismal theorem?
Sorry? Oh, the dismal theorem. How many of you know Marty Weitzman? Nobody? Yeah, you know Marty Weitzman. Let me start with the sad story. And I really want to tell that sad story. You know, the Nobel Prize of Economics 2 years ago was given in the field of environmental economics. It was Nordhaus, Bill Nordhaus, together with Romer. Romer was the previous chief economist of the World Bank, I think, a different area. Nordhaus is one of the founding fathers of CO2 pricing and so on. Weitzman was an extremely interesting person at I think was MIT, I think, or Harvard, who did a lot of interesting work also, but more on the quiet scientist side, with more questioning. Can we use this method really in this context? Let me now tell the very sad story, and it's published, so that Weitzman, after the Nobel Prize was given to Romer and Nordhaus, not long after, he killed himself. He was very disappointed, and somehow he said, the fact that I cannot produce the same quality of work now anymore made him very unhappy, I think. It was a very sad story. Now, he formulated the concept of Dismal theorem. And the dismal theorem, and this goes back to your question also, the dismal theorem is, I can make it a theorem in mathematics if you want, about parameter uncertainty and mixing and all that, and getting Pareto tails. But early on, the lady with the operational risk question, cyber risk, the first paper is paper number one in volume number 1 of the Journal of Operational Risk with 2 of my colleagues, is about infinite mean models for operational risk, because we were analyzing data of operational risk, very few around in those days, the same environmental, the same with nuclear losses, where a good statistical analysis was pointing into an infinite mean model. Now, I'm the last person to say that an infinite mean has a realistic meaning, because the world is finite, 10 to the power 85 electrons, I don't know. But the fact that statistical analysis is pointing into such very heavy-tailed losses, cyber, operational, nuclear, environmental, that has an important consequence, and that was one of the main points of Marty Weitzman, that classical economic thinking breaks down. Diversification breaks down. You better hold 1 than 2 of these risks. That already knew Mandelbrot. He used the Cauchy model for that. Classical, and that's much more his point he takes, classical cost-benefit analysis breaks down. And that became a huge discussion between Nordhaus, an interesting, scientifically friendly discussion between Nordhaus and Weitzman. And I think Weitzman, for me, I think he pointed to the very right issue there, that in these losses like environmental losses, nuclear losses, we really have to look at these questions very, very differently. And even at some point have to decide, no, society can, well, in the case of, well, in all cases, we cannot bear it. We cannot insure it. And that's, I think, and that society will have to look for. And I think it's so sad, and that's why I mentioned the intro about the death of Weitzman, that this brilliant mind that really pointed to a very important issue is not there anymore. But the dismal theorem, you can look for it and look at the interesting discussion, but the point is the breakdown of standard economic thinking, cost-benefit, diversification, etc., in the face of these extremely heavy-tailed risks. And I can make it a theorem if you like, but that's not so interesting. That's a dismal theory. It's dismal.
Thank you. Any further questions? I have a couple of questions, Paul, particularly what you said in the end, that we should publish uncertainty. You seem to be much more optimistic than I am. When I think when politicians would hear there's a 95% chance we get between -1 and 8, they will go for the -1 and say, hence, we don't need anything to do.
Yeah, that's well, then we have to educate the politicians, I think. No, I know it's an issue, and I don't take...
President Trump definitely believes in the -1.
Oh, yeah, he goes for the -1, I think. Yeah, it's a fact. What shall we do? And I really feel sorry for we have at ETH some like Mr. Knutti and so my colleague Knutti, Reto Knutti, very, very famous environmental scientists, and I think they have a hell of a life. I mean, they know there are thousands of deep papers with ice cores, with whatever measurement you take, it's pointing in a direction. Also, you see the sea rise. You don't have to do difficult stuff. You can look at the Dutch sea rise. There are serious issues there. And yet then suddenly comes an expert somewhere and says, no, I don't believe that, and this and that, and then, of course, we listen to that person. I think it's a sad thing of society, and I think, I don't want to end on too negative note. But I think it's for the young people, you really have to fight against that. I think it's miserable if we give up standing for scientific education, scientific beliefs, and saying, well, this is what science brings. And as I said also in the end, also with the dikes, that the Dutch government in the end said, okay, well, we don't go for 6 meters, we go for 5. Well, there can be a heated discussions, but in the end, that's the case. They may say to me, well, listen, 5.5 meters completely will ruin the country. We don't have the money. Well, what shall I do then? So the discussion has to take place, I think, and it's a sad thing, but we cannot avoid it. And by the way, society is running more and more into these difficulties. I mean, it's clear with the societal risk-like environment, social networks, you just named them. I mean, there's so many interesting things that have been going on, but also rather difficult things to model and to take decisions on. Anyhow, I still have a lot of hope.
Good, thank you very much. Any last question, last remarks? If not, then I'd like to thank Paul for